Hello everyone and welcome to this presentation. My name is Patricia Adame. I am the Senior Application Engineer for Saint-Gobain Tape Solutions, focused on materials for EVs and battery packs. Today, I would like to review the main functions and challenges that cell-to-cell pads, also known as compression pads, face inside a battery pack environment. And of course, I will introduce the solutions that Saint-Gobain has to offer in this field. So let's get started. What are the main challenges for a cell-to-cell compression pad? I am going to start with a thermal performance. The pad should perform within the battery's pack operating temperature range, and if possible, provide some thermal protection. You can find in the market there are different compression pads materials formulated with a variety of flame retardants to enhance the thermal resistance. There are even composite materials that can offer thermal protection during a thermal runaway event, where temperatures can reach more than 800 Celsius degrees based on the cell's chemistry. The other challenge is mechanical performance. Compression pads should provide cushioning to the cells, but also have resilience and rebound capabilities to adapt to the cell's expansion and contraction during the charging and discharging cycles. Third, electrical performance. Electrical isolation is also a must-have property, since engineers are designing a reliable battery pack, and therefore they should select materials that would protect against known failure modes, such as electrical shorts. And last but not least, cell-to-cell pad assembly should be smooth. So it is not only about providing a solution or a material that will perform during the application usage, but also is its manufacturability or assembly, considering automation and cycle times. These two graphs were taken from a technical article. They explain how a lithium-ion cell expands or breathes during the charge and discharge cycles. Depending on the cell's manufacturers and the cell's format, so it could be either a pouch or a prismatic can, the swelling might be minimal or more pronounced. However, that swelling is irreversible and it impacts the battery's performance over its lifespan. In that same technical article, it was addressed the importance of considering a cell-to-cell pad in a battery pack assembly. It would not only help with the challenges previously mentioned, but it was found out that the cells not only need a material that can provide the cushioning, but also provide some pressure to the cells themselves to improve their lifespan. Having no pressure at all, like this blue curve is showing, or even a higher pressure than the cells can withstand, will result on a shorter cell lifetime. So it is critical that engineers know which would be an optimal external pressure, either a target value, a range, or a not to exceed pressure on the cell to lengthen its lifetime. Saint-Gobain Tape Solutions team have done an extensive market analysis and understanding these challenges and pain points for battery packs manufacturers, we have developed product lines to overcome them. From really soft polyurethane foams with some level of flame retardancy, such as UL94 HBF, to stiffer polyurethane foams such as PF200, and even silicone foams that will provide a higher thermal performance and UL94B0 rating. Most of these product lines can be manufactured locally in our three main regions, North America, Europe, and Asia. All of them are provided on master rolls that can be die cut to a specific dimension and shape based on the customer requirements. We offer standard thicknesses, but we understand some designs are quite unique and therefore require unique solutions. So we work closely with our customers to better understand the application and we are able to provide the level of customization each application may require. As mentioned in the previous slide, we have a wide range of soft and stiffer polyurethane foams. As you can see in this stress versus strain curve, we have soft materials for pouch cells, a little stiffer ones for prismatic, and even materials or foams for solid state batteries that usually need to be stiffer. The main things that we can tailor on these product lines are density, thickness, and surface finish, meaning that it can be tacky, non-tacky, or we can even coat pressure-sensitive adhesive on one side. We have great commercial and technical teams willing to learn about your specific needs and come up with a solution that best tackles the most critical performance requirements. This is another visual aid to better categorize our product lines. From soft polyurethane and silicone foams for pouch cells, our softest polyurethane foams will be the PF27-200, to our little stiffer materials such as PF47-330, and our stiffest polyurethane foam PF200 for solid state batteries. Each colored dot, represents a compression strain from beginning of life up to end of life, based on the strains that we've seen in some applications, and also considering the highest compression strain that a material can withstand before having some structure damage. We're also delighted to offer value added to our customers instead of only being known for a high-performance foams manufacturer. Therefore, Saint-Gobain Tape Solutions technical team has been working on this modeling tool called Maxio. This tool can provide material suggestions based on the battery pack unique design parameters, such as the assembly speed, number of pads or number of cells in a module or array, the beginning of life pressure, the cell expansion, and the end of life pressure. We do have a standard stress versus strain curves, either tested based on ASTM or ISO methods, but we have learned that each design comes with its own challenges. So this tool takes into consideration those specific parameters in the application, so we can offer the best material at the optimal nominal thickness each time. I don't want to get into the details and the math behind this tool, but this tool was developed considering the compression curve as a function of compression speed. So we are adding a parameter called strain rate rather than just following a compression speed. So the tool can suggest the optimal uncompressed or nominal thickness for the compression pad, taking into consideration the assembly speed and the number of cells. This tool can combine different materials if a composite or a layer solution might be the best fit depending on the application requirements. So we can either get the stress versus strain curve combining two different foams, or a foam with another layer with another material such as mica. For the remaining of the discussion, I'll just like to showcase the resilience of our Norseal PF27 and PF47 product lines. Most of the compression curves are done at room temperature, but we know battery packs have a normal operating temp of -20 Celsius up to 60 Celsius. So we were able to test these two product lines at those temperatures to better understand what could happen to the mechanical performance. These graphs are showing a hysteresis curve of the foams tested at -20, the black curve, at room temperature, the blue curve, and at 60 Celsius, which is the red curve. You can see how close the room temperature and the high temperature curve are on both the Saint-Gobain products. We even added sample of our competitors' polyurethane manufacturer, and the foam, when tested at 60 Celsius, became really soft, which means it lost its resilience to rebound. And in the application, it could result in mechanical issues inside the pack. Not satisfied only with a hysteresis curve, we wanted to do a fatigue cycle with the same Norseal PF27 and PF47 foams. Due to the resources that this test needs, we only tested one density, which was the 250 kilograms per cubic meter. The test consisted in compressing the samples from 0 up to 80% strain, up to 3,000 cycles with a test speed of 5 millimeters per minute. We were delighted to see the resilience of our products. Even after 3,000 cycles and at these different temperatures, the material retained its mechanical performance and the loss of thickness was minimal from the first curve to the one after the 3,000 cycles. Testing at -20 Celsius is tricky just because the material, when it's exposed at this temperature and compressed at high strain values, just takes longer to recover. This slide is showing our PF47 250. So you can see that both curves before cycling and after cycling at these three different temperatures are really close to each other, and also the thickness loss or change before and after testing is minimal. For the last slide, I just want to emphasize on our core value, which is customer centricity. We do not offer just a material solution, but a holistic technical support, since us being expert handling foams can provide ideas on the best way to handle them for assembly and even automation. We are always looking for partnerships, even with automated companies, to better understand their technologies and develop tailored solutions or some aids to ease assembly of our current standard products, since we know cycle times are critical in the automotive world. For the last project we worked on, the team developed a vacuum solution. You can see it in this picture. Since the application was so unique and it was a cell-to-pack design, the foam had to be in a compressed state so it could be assembled. This is just another example of the level of customization and the deep in understanding that we want to have with our customers. This is all I have for today. Thank you very much for joining me. It's been my pleasure to showcase our capabilities, and I am looking forward to solve your unique challenges. Please visit our website or even reach out to me. You can see my contact information in this last slide. I would love to hear about your projects and your specific needs. Have a great day.